Hi, welcome to QuBites, your bite-sized pieces of quantum computing. My name is Rene from Valorem Reply, and today we're going to learn how to best deal with the complexity in quantum computing. And for this, I'm very honored to have a special expert guest, Professor Robert Wille. Hi, Robert. Hi, Robert, actually, and welcome to the show. How are you today?
Hello, Rene. Yeah, I'm fine. Thanks for having me.
Awesome. I know you were actually also a guest professor in my hometown, Dresden, where I'm actually recording from right now. And in general, you have a very impressive background in the field. So tell us a little bit about yourself and what have you done in the field of quantum computing, but also physics and math and all of that stuff.
Sure. So yeah, indeed, I spent half a year in Dresden, and it's a beautiful town. So really enjoyed my time over there. But in the meantime, now I'm in Austria, actually, more precisely in the Linz area, and there I'm a professor at the Johannes Kepler University in Linz. And additionally, chief scientific officer and a technology transfer company called SCCH, which stands for Software Competence Center Hagenberg.
Mhm.
And in those both jobs, I am developing methods and tools to aid engineers in the design of complex systems, such as software systems, hardware systems, systems composed of both. And also, I guess this is going to be the major focus of our chat today, also systems like quantum systems, quantum algorithms, and stuff like that. So, and maybe in this regard, maybe I can also outline directly unveil that I'm not a physicist or an electrical engineer. I'm a computer scientist. So everything I'm saying here right now is from a computer science perspective.
Yeah.
And so although I have a huge interest in, of course, when you work in quantum computers, you have to have an interest on quantum physics and physics in general. But to be honest, I'm a layman in physics, but obviously have an interest in that. But my main training is computer science.
Yeah, just like I'm also a computer. I actually studied media and computer science, so I have also a little bit in that area. But yeah, definitely. But when I was studying, I guess you weren't a professor then, because like I'm quite old now. So, but anyhow, so let's dive into our topics. You already hinted a little bit at. Like you're an expert for automatic methods for design and simulation and verification of these complex systems. And like you said, that also includes, of course, quantum computers as they are very complex systems, right? And so tell us a little bit, what are some of the challenges, for example, when folks are designing quantum circuits? Like how can you, what are the challenges really there in these complex systems when designing quantum circuits?
Well, there are many challenges. I mean, obviously, the entire paradigm changes, and not so much only the paradigm of how we program computers, but actually the entire paradigm how we are supposed to think about it, right? I mean, of course, listeners of your videos, of course, know quantum computers is not only about zeros and ones. So in the classical world, we work with zeros and ones, but with quantum computing, we suddenly got the superposition of both, the entanglement of both, and in addition to that, lots of many quantum mechanical effects and operations, for example, are suddenly unitaries, right? So when we developed classical algorithms, classical systems, although here you still had to learn programming languages and had to get used to the tools, but you still knew, okay, in those classical languages and classical programming, you still did something like 1 plus 1 is 2. Now, if I ask my students, do you know what a unitary is? A unitary operation. Of course, in the beginning, nobody knows because we're not that sort of used to it, right? So the main issue is indeed that first, of course, we have to learn these new programming languages and paradigms. And this is, I mean, when you start as a computer scientist student, you have also to learn Java and Python, but you still work with the computing paradigm which you're familiar with. Now you have to learn all those new languages and all those new tools. And on top of that, those tools suddenly work with these strange things like, as said, superposition, entanglement, totally different kind of operations. So this is a huge challenge just to start with. And then on top of that, also, and I don't want to discourage people from that, but everything gets more complex in the sense that working with zeros and ones is still sort of doable. But if you, for example, if you have an electrical signal in a hardware, you have the signal being assigned to 0 and 1. If you have a qubit in quantum computing, it could be you need to represent suddenly an exponential number of amplitudes to represent the state of it. So complexity is significantly increasing. And again, don't want to discourage anyone because this complexity is also what makes it fascinating and also what sort of, I mean, it's like puzzle solving. It's getting harder, but it's really rewarding once you mastered it and once you dealt with it. So I guess those kind of things, the different paradigms and the complexity are the main challenges.
Yeah, I love how you put it beautifully, like that it's an exponential factor of amplitudes actually in your qubit. Or also sometimes I hear folks saying like, so with bits we're dealing with digital information, like 0 and 1 basically, but qubits can rather represent analog states, right? And that is actually also a nice part. Also, sometimes I think about it from a philosophical standpoint, right? I mean, this is how nature works in the end, right? Nature is probabilistic and nature is analog and not digital, and so we can get closer how our universe actually works. And so that is so fascinating, like you said, right? Also coming from computer science background, I mean, of course we are kind of geeks and nerds, right? So we love physics and quantum mechanics. But following up on these quantum circuit question and the simulation actually of these quantum circuits, so why is the simulation of quantum circuits so important, and what work are you doing in that space with your group?
Yep. So simulation, the main idea of quantum circuit simulation is, as the name suggests, to simulate a quantum algorithm on a conventional machine. And now you might ask, why should I do that? Why not directly executing the quantum algorithm on the actual quantum computer? And of course, this is something at the end of the day I want to do. But right now, of course, access to quantum computers is still restricted. So you don't want, to trial and error. You don't want to debug necessarily your main idea of an algorithm on a real machine, because then you sort of using the system, and some other colleagues cannot do that. So it makes sense if you develop your quantum algorithm. It makes sense to develop that on a smaller scale on a classical computer, simulate it, and then sort of fix all the major bugs there, so that you don't waste precious quantum computing time. But let's assume even if we would have no restrictions on quantum computers at all anymore, if we have every one of us can have as much as possible time on a quantum computer, even then I think quantum circuit simulation is needed, because the quantum computer does not give you full access to all the information. You might know when you execute a quantum algorithm, at the end of the execution, you measure your result, and then with certain probability do you get some output. And of course, you want to design your algorithm that you get the desired output with a higher probability. That's why we have in these algorithms things like amplitude amplification. But in order to really check that, you need access to the precise information of the quantum state, which the real quantum computer cannot give you. But quantum circuit simulation on a classical machine can do that. It can give you all the information, and this is something what you need in order to develop algorithms. And obviously, this is also I always like obviously we can do this on a classical machine just with small algorithms, right? Because if I could execute all quantum algorithms on a classical machines, if I could simulate that on a classical machine, I wouldn't need a quantum computer. But to develop those and to understand how it's work, also to understand error effects, to analyze error effects, simulation is still the key, and it's going to be the key, because the real quantum computers does not give you all the information you would need to maybe really nail your algorithm.
Yeah, totally makes sense. So you're actually can understand it better if you simulate it, and then can build better real quantum computers or understand them better. That totally makes sense. In fact, actually, in season 3, episode 9, I talked with Christopher Rene, who works at Microsoft in the Azure Quantum team, and they also work on a noisy simulation or noise simulation, basically getting closer to simulate how the real noise in the quantum system actually works, and so they can simulate it already, and then just like you said, understand it better in this kind of simulated environment where you have full control and it's more of a deterministic behavior. And so yeah, no, that makes totally sense. um, of course, right now there's a big challenge, also, to make the quantum field and also especially quantum programming and so on more approachable, right? It's still, a lot of that you still need to target specific hardware if you're dealing with quantum computers with the hardware, basically, or you can use middle layer kind of tooling, right? Like Azure Quantum or the QDK or Qiskit and what have you, right? There's a bunch of things available. But from your perspective, how can quantum hardware and software design be made easier and approachable for more quantum computing experts, or not just for quantum computing experts, but actually for computer scientists, for example?
Mhm. Um, Again, tool support and design automation methods. I mean, obviously, I'm biased here because that's what I stand for, but I really believe what we're doing, developing those tools, those methodology, is key of making it more accessible. And I'm really confident about that, because kind of we are simply redoing history here somehow. If you check out classical computers again, a couple of decades back, we had only electrical engineers were able, to put these computers together and to actually use them. And then, of course, it was not accessible at all. It was restricted to this peer group of experts. And then we developed programming languages and tools and stuff like that. And suddenly we substantially increased accessibility, but still probably more for guys like us, for these geeky guys who love hacking and stuff like that. And if you check out, however, the development, right now we're extending it further. And right now, I mean, it's maybe a little bit stereotype, but right now I really believe we are really getting to a situation where literally everyone can create a next dating app or a next system on a classical computer. So that's how we manage to improve accessibility in the classical world. And obviously, this is something we need to accomplish in quantum computing. In quantum computing, we are just at the beginning of this development. I still remember I work in this area since more than 10 years. And at that time, it was mostly the physicists and maybe the theorists and the mathematicians who worked on that. Maybe some computer scientists, but definitely not mainstream. Now we've got the first tools. We are still not there, but we're increasing the accessibility. And now we are developing, as we did in classical computing, more programming language, better tools, better methodologies. This is where we get to it. And if I may, this is, of course, to make it more accessible for quantum, for computer scientists or for end users. But also what we also need to accomplish, in my opinion, is we need much more bridging between the communities. The computer scientists need to talk to the physicists, need to talk to the end users. We really have to, bridge these communities together. My feeling right now, and this is a typical development, but everyone is in his own bubble right now. We have to put those together. And this is also something which could help making this whole technology much more accessible for everyone.
Makes a lot of sense, and this is also the goal of the show here, right? Making quantum computing more approachable. And so, thanks for being part of that, and sharing your story about how to make quantum computing more accessible and getting it outside of the or not just having the focus on the pure scientific and research in quantum computing, but again, opening it up for many, many more folks, because we need diverse skills in this field to actually grow it, right? We're already at the end of the show, but thank you so much, Robert, for joining us and sharing your insights. That was very much appreciated.
Thank you very much. Was my pleasure and was fun. Take care.
And thanks everyone for joining us for yet another episodes of QuBites, your bite-sized pieces of quantum computing. Watch our blog, follow our social media channels to hear all about the next episodes. And of course, you can also watch the previous episodes there. Take care and see you soon. Bye-bye.